Hi, welcome back, everyone. This is the lecture 9 of the Deep Neural Networks course, and we're going to continue with recurrent neural networks. And I thought that I will start by just repeating some of the key points from the last lecture, partly because so just a reminder might be useful, and also because I want to refer back to some of these ideas later on in the slides, so it's going to be useful. And this is also a good time, the next couple of slides, if you have any questions that you don't understand about the basics of RNNs, or any comments or some things that you want after the previous lecture, or just in connection to this introductory couple of slides, then please just put it in the chat, and Neil and Nick might answer it, or I'm happy to also take some questions. So this was the figure that I've put up about recurrent neural networks last lecture. And just the key point here is that now the input to the network, which is at the bottom, is a sequence of symbols or sequence of values, and we also kind of call these individual symbols time steps, and time in that sense goes from left to right as we progress through the sequence. And from bottom to top, we have various layers of this recurrent neural network. So here I show a 2-layer recurrent neural network with some outputs y coming out at the top. And the main action that's happening in a recurrent neural network is the hidden state update rule. So these blocks here are the hidden states. H12 is the first hidden layer activation at time step 2. And this is going to be calculated from the activation at layer 1, so the same hidden layer, but from the previous time step. And it's going to also incorporate some new input x2 that we are seeing in this time step. And the subsequent layers work exactly the same way, except that they don't take the raw input sequence as their input, but instead they are taking whatever the hidden state is at the lower layers as their input when they are calculating their state updates. And as I said, you can choose when and how you want this network to generate outputs, or what you consider the network's outputs. Here I'm showing a situation where we produce some output sequence. So for every element of the input sequence, we produce something, a corresponding output. But it might also make sense to just produce a single output at the end of this, for example, if you want to classify a sequence. One important thing about RNNs, and I'm not sure that it came across, is that when I'm drawing these arrows, this update rule that determines what the next state is going to be given the previous state is something that is invariant over time. So these arrows that here show the computation of the next value of the hidden state from the previous hidden state, that function doesn't change over time. That's something that's constant over time. Hidden states themselves change, but how we calculate the next state from the previous one is something that is fixed, which means that even if you apply this RNN to a very long sequence, so this graph, this unrolled computational graph would get bigger and bigger, but the number of parameters describing the RNN would not grow. It stays constant. And this is why this is a great parameter efficient architecture that you can apply to arbitrary length sequences without growing the number of parameters. The actual functional form of the update rule is very consequential in RNNs, and we talked about this most basic or naive form of the update rule, which is inspired by the usual multi-layer perceptron type architectures that we've worked with before. So to calculate the next hidden state, we take the previous hidden state and the input, linearly transform them and add some bias, and then we apply a component-wise nonlinearity. The problem with this, as I mentioned in the last lecture, is that if you try to apply an RNN with this update rule, it's not going to work well. And the main problem that we identified was the exploding or vanishing gradients problem. the fact that there can be situations where essentially the hidden state starts to depend less and less on whatever happened early on in the sequence. So this process, if you consider the hidden state of the RNN its memory, it has a very, very short memory back in time. One of the ways to overcome this limitation of memory is to introduce these gating mechanisms. So here are the update equations for the gated recurrent unit. And one new type of operation that we haven't seen before, which we introduce, are component-wise multiplication of different activations within the network. And one thing that I maybe could have done a better job explaining is that why this particular form of the update rule, like what is the meaning of ZT times the previous HT, the previous hidden state, plus 1 minus ZT times something else. And in order to motivate this particular choice of a formula, if you may well have done this several times when you were coding already, but for those of you who did not recognize this the first time, this is a way to implement branching logic in maths or in algebra. So if you have something in your code, R is a binary, like a Boolean variable, and you have something in your code like if R, then return 5, otherwise return 3, you can equivalently implement the same thing using maths by saying R times 5 plus 1 minus R times 3. Assuming that the Boolean variable is implemented such that the value of 1 signals a true value and the value of 0 signals a false value, which is often the case in most programming languages. These things are equivalent. So these two things are equivalent. So if you go back to this GRU unit activation, we can see that that's exactly what's going on here, component by component. This is essentially saying if the value of Z is 1, then do not update the state, which means copy over whatever the hidden state was in the previous time step. If, however, its value is 1, then use this alternative value to update the hidden state. And so essentially that's what's happening inside the GRU unit. You have these two variables, which are called the update gate and the reset gate. I keep forgetting these. And these essentially work like if statements in the network. The main difference here from an if statement is that these are not Boolean values. These are not zeros or ones. These are values between 0 and 1. So instead of just either taking ht or h tilde t, here we can, if z is somewhere between 0 and 1, we are linearly interpolating between the two values. So it's a differentiable relaxation of conditioning logic here. And what this conditional logic allows the GRU network to do is to remember certain hidden states a lot longer than it would have normally remembered, because it can basically just decide to keep this ZT as 1 in all the time steps, and then it can keep the same hidden unit and essentially propagate it forward in time without further nonlinear processing. I'm going to look at the chat if there's anyone, any other questions.
Yeah, for instance, there was one that's I think it's quite interesting because it's sort of the direction the course is going in. Killian says, how does the RNN perform compared to CNN architecture? It seems the RNN architecture is highly computation expensive because of all these nodes connected to each other.
That's, I think, true, although maybe Nick has more direct experience to this. There are main differences. There are similarities and differences in the RNN and the CNN. There is one similarity, which is that because the updating logic is the same at all time steps, in this sense, the RNN architecture is also some translationally invariant. So if you kind of translate the input sequence and apply the RNN, the output sequence translates with it. So that kind of invariance property happens in RNNs as well as in convolutional neural networks. But I guess you're right in that a CNN is usually more computationally efficient to use. One difficulty with using CNNs is that an RNN deals with varying sequence size much more naturally than a convolution. You can, of course, apply convolution to an arbitrary sequence length, but if you want to classify sequences of arbitrary length with a CNN, you have to do something very smart about pooling logic to make sure that independent of the size of the sequence that you started with, so in this length at the bottom, you end up with just a single classification output, which in the case of the RNN you can always just consider the final output. With the CNN, this is a little bit trickier.
I would just add an interesting thing is that the bits and pieces that go in RNNs and all these different types of variations are actually fully connected layers. So when they implement them in PyTorch and so on, so unlike CNN, we have quite different logic. It's implemented quite differently. These are just like tiny pieces of fully connected networks, all kind of arranged together to build the gates and so on. So
yeah, but in a way, in order to process the activations on the first hidden layer, you kind of have to do it sequentially over time. So you have to first calculate the stuff at the left-hand side and then the second time step and so on. You can't really easily parallelize these. Whereas if this was a convolution over time, that is a highly parallelizable operation, and that's easier to do. One example so there was a time when Facebook AI research and Google research were battling it out, and Google research were kind of putting forward LSTM and recurrent neural network based architectures, while Facebook AI research, which was led by Jan LeCun, was trying to do the same things with convolutional neural networks. So very often, if you find some problem being solved by LSTMs, you will find a corresponding paper, very often from Facebook AI research, solving the same problem with convolutions. I think the one major example where Google came up with something that was convolutional, where it might have been more natural to think about RNNs, was WaveNet, which is a model for audio data. And that's a convolutional neural network using dilated convolutions.
Was that Google or DeepMind?
That was DeepMind, which is, yes, that was DeepMind.
And actually, I do want a little follow-up question on that, because there's this sort of history around, I guess, whether the preferred frameworks handled recurrent neural networks as well. For instance, I remember something vague about that. I wonder if you knew something more about, like, my understanding was at some point, TensorFlow and Torch had different capabilities in handling these different length sequences, and that seemed to oddly affect some of this.
Yeah, so another thing that we didn't talk about is that when you do mini-batch gradient descent, you want to consider multiple inputs at the same time. So if you handle, if your inputs are individually sequences and they are of different length, then problems can arise by batching together very long sequences and very short sequences, because you want to fit them inside a big tensor that is like square shaped, and you have a bunch of different length sequences, then you're going to waste some of the time. I don't actually know too much about what the differences were, but I can imagine that because of the rigidity of early TensorFlow, it had a so-called static graph framework. So you had to compile the computational graph ahead of time and then give it some data. And when you compiled the computational graph, you had to specify the length of all and the dimensions of all the tensors. TensorFlow early on was very rigid in terms of the sizes of tensors that you could use. Whereas PyTorch early on, and Torch, which predated PyTorch, was much more flexible. You could essentially, you didn't build the computational graph ahead of time. The computational graph was built dynamically as you were executing code. So in this case, for example, if you were processing a longer sequence, you would dynamically build a longer computational graph or a larger computational graph. And so this allowed much bigger flexibility in PyTorch to handle all these kind of varying length inputs and things like that. That was probably useful for RNNs. That said, I'm not too familiar. Like there might have been other differences which made one framework better suited for one type of architecture.
I think that was the thing that, as I remember it, and I'm also not expert, but I think that the main point is that these frameworks have significantly affected how people do things. I mean, because there are things like TensorFlow is easy to deploy on mobile devices. I think that may be true for PyTorch now as well. But you see this interaction between what the available frameworks are, the available hardware and everything else, and what things people are deploying in practice.
Yes, yes. So I think, yeah, so there was a big, I think, battle between PyTorch and TensorFlow, and they both took certain things from one another. So TensorFlow was initially a static graph framework, but then they introduced eager mode, which is a dynamic graph way of working. So now you can do a lot of the things that you could do in PyTorch very similarly in TensorFlow as well. It's a little bit less natural because it's more of an afterthought, but I think since TensorFlow 2.0, it works a little bit more flexibly. And vice versa, PyTorch took some of the ideas from TensorFlow in terms of, you know, better production-ready code and being able to export the models for easy deployment in high-performance environments and things like that. But yeah, I think that nowadays there's not a huge difference between PyTorch and TensorFlow. You can probably use either. My impression is that TensorFlow is still more widely used in industry because it has more, you know, more like an enterprise type API. It has a more foolproof API to do certain things in. Anyway, that's an aside about these frameworks. So assuming there are no more questions, I wanted to talk about this other concept, which is how recurrent neural networks are in a way similar to very deep neural networks. So I've drawn RNNs, and most people draw RNNs in this form where time goes from left to right. So the sequence length determines how the horizontal size of this figure, and then depth of the network goes from bottom to top. But you can turn this on the side and also consider the RNN for a very long sequence as being essentially a very, very deep neural network, in the sense that if you look at the relationship between the very first, I rotated this node so that it's at the bottom. And so I hope people won't get confused. So this node here became that node here. And this node up here became that node up there. So if you consider the relationship between the very first entry in the sequence and the very last output, you can see that there are many, many layers between them. And depending on the sequence length, the depth of this computational graph is actually dynamically changing, and it can be very long. So it can be hundreds or thousands of time steps, or hundreds or thousands of layers, essentially. What's different from a very deep neural network, for first of all, each of these layers here does pretty much the same thing because it uses the same state update equation. And the second thing that's different from a very deep neural network is that these layers also receive additional inputs, the next symbols in the sequence. But a lot of the problems that we have discussed with RNN training, like vanishing and exploding gradient problems, also appear in very deep neural networks that aren't necessarily RNNs. And this was probably true around 2015, is that around the time we already started seeing very big success stories with deep neural networks, but the neural networks we used weren't actually all that deep. They maybe had tens of layers, not hundreds or thousands of layers. In fact, one of the biggest networks or deepest networks at the time was VGG19, which was a 19-layer COMNET. And this was, I don't remember if Nick had this in his lecture, And this is actually a very, very simple ComNet that has only 3x3 convolutions. I'm going to show a picture of it. But it only had 19 layers. And if people wanted to go any deeper than that, then, well, practically you might go into an exploding vanishing gradients problem, which you can solve with various optimization tricks. Or, but even if you solve those vanishing gradient problems, you see that the performance actually degrades with depth. Going any deeper did not seem to improve performance. So we hit a wall in terms of the depth that we could achieve. So here are examples of very deep networks. I've rotated this figure because it's from a paper, so it made sense to put it vertically here. But when I put it on this slide, it's rather awkwardly shaped. At the bottom, you see the VGG19 network, which I talked about. On the left-hand side, we start from the image, and all these colorful blocks are different 3x3 convolution layers. And the different colors denote different feature map sizes. So between, say, the purple and the green layers, there is a pooling operation which reduces the feature map size by 2. And this featured in Nick's presentation as well. So after a bunch of these convolutions and the number of pooling layers, 5 pooling layers in total, you end up with a feature map small enough to actually consider it a vector. It no longer really has the shape of an image anymore. And towards the end, you apply 3 fully connected layers. So this is at the end of this network is a 3-layer multi-layer perceptron, essentially. And this is the VGG19 network. An interesting note on this network is that convolutions are so parameter efficient that more than 90% of the total parameters of this network are in these final 3 fully connected layers. Only a very handful of parameters actually parameterize the first 16 layers of this network. So this is, by the way, a network that you can download a trained version of from the VGG group, which is the Visual Geometry group in Oxford. So you can play around with it. You don't have to train it yourself. You can see what it does on different data sets. So it would be natural to extend the VGG network to an even deeper network. So essentially just adding more convolutions in each layer. And this is showing a 34-layer generalization of the VGG network. It turns out if you do this, you can train it. You don't get into optimization problems, but in practice, this network is not going to do very well. The error rate of this network is going to be way higher than the error rate of the much shallower network, the 19-layer network. On the top is shown a different network, which is very similar to this 34-layer generalization or 34-layer convolutional network, but now it adds these extra shortcut connections. Each convolution layer here is fed into not just the directly next layer, but there is a shortcut created between this layer and 2 layers down the line. And you can see this repeating pattern of these shortcut connections between the input and the output. And it turns out that if you add these shortcut connections, suddenly this deep network is going to be able to learn much better than this feed-forward network that does not have these shortcut connections. That's called deep residual networks, or ResNets for short. This is a very simple idea, but it has been very influential in allowing deeper networks to be built. The ResNets have this simple building block, which is called a residual block. So you can see that a ResNet is made up of many of these blocks put on top of one another. And in each block, we have 2 paths. So the input to the layer comes at the top here, X. X is first put through a weight layer, which is either a convolution or it can be a fully connected matrix multiplication. Then there is a ReLU or another activation function of your choice, and then another linear transformation. So it's linear transformation, nonlinearity, linear transformation. And then this transformed value of x gets added together with the input to this residual block itself. So there is a shortcut connection which takes the input to this residual block and adds it together with the output of this nonlinear transformation. The consequence of this is that if you set all of these weights here to 0, essentially what the residual block does is it doesn't do anything. It doesn't change its input. It copies its input to its output. So it implements the identity mapping by default. And all what the parametric part is doing is it changes the behavior of the residual block compared to the identity. So instead of implementing the identity, it implements identity plus something else. And it's called residual because the parametric part of this network model is not the output of the module, but the residual, which is the difference between the output and the inputs to the model. So this simple idea for ResNets allowed for much deeper networks to successfully train. In the first paper on ResNets, they showed 101 and 152 layer networks. The particular numbers are a side effect of the image size and the size of the convolution kernels working out in a specific way. It turns out that performance increases with depth. So the fact that we bottomed out the performance at a 19-layer VGG network was not a fundamental property of deep networks. It was just a consequence of not being able to train deeper networks successfully. This ResNets at the time, this was, I think, 2015, set a new record in a bunch of benchmarks like ImageNet and Coco, and they are used almost everywhere now. So whenever you use deep networks, more likely than not, there is going to be residual blocks instead of just normal feed-forward layers in all the networks. A nice picture illustrating why ResNets might be so successful is the one that I've shown, that I've put on this slide. And consider a residual network with just 3 residual blocks, which is shown on the left. So each of these residual blocks has a path, which is an identity mapping, and a path which implements some kind of nonlinear function. Here it's just shown F1, F2, and F3. And you can consider the number of paths between the input and the output in this network. And you can notice that in each residual block, you can make a binary choice as to, if I want to walk from here to here, I can either choose to walk on the identity path or I can walk through the nonlinearity. And I make this binary choice in every single residual module. So in total, there are 2 to the L different paths that I can take from the input to the output. And because these are all of these paths are essentially summed up, so these nodes here sum up these different paths, I can equivalently consider this network as being the sum of these exponentially many different paths between input and output, which are exponentially many different neural networks that are all summed together to produce the output from the input. So for example, one of these, so there are 8 different neural networks here. The first neural network at the top does nothing. It's essentially just the identity. It just copies the inputs to the output. Then I can take a route through F1 and then through the identity links. So that's a very shallow neural network. And then there is also a path which includes 3 nonlinear mappings. So this is a very deep path, a path which has very deep function transformations. So you can think about ResNets as, in a way, creating an ensemble of exponentially many neural networks with varying depth. So some of these neural networks will be very shallow, just have a few layers of nonlinearities, and some of them will be very, very deep. And this may partially explain why it's possible to train very deep residual networks, because some of the path between the output and input remain shallow even as we make this residual network very, very deep. And there are, of course, a bunch of generalizations of this idea. One of them that I show here. I don't know if that's, okay, sorry. I just got a message from Neil and I'm not sure. So the one generalization of this is dense nets, which are densely connected neural networks. So you can see here that a dense block, instead of just having one shortcut connection that skips layers, has all the possible shortcut connections between non-adjacent layers. And that's sort of one way to increase the performance even further. So coming back to RNNs, why is this relevant to understanding how LSTMs work and how these various versions of RNNs work? You can think of LSTMs or the GRU units that we talked about before as essentially creating shortcuts over time. And these gating mechanisms that we introduced allow information to skip processing for a number of time steps, and thus it is preserved unchanged for several time steps, potentially in the hidden states. In an RNN, the gating mechanism is data dependent. So whether or not you skip a layer or you skip an update for a hidden state is dependent on the data itself and the hidden state of the neural network. And this means that the shortcuts that are created in an LSTM or a GRU network are itself data dependent. So this network can kind of make up its mind about creating these shortcut connections over time that allows information to pass unfiltered over multiple time steps. One pointer that I wanted to put in here is a very excellent post on Distill, which shows the behaviors of various RNN variants. So I'm not going to go through this in detail. You can hopefully find this link and play with it yourself. One thing, you can think of this as an extension of this toy example that I looked at last time with the Colab notebook, calculating the gradients of the hidden unit, the final hidden unit activation in an RNN with respect to the input sequence, and visualizes these gradients for character-based recurrent neural networks. So you can play around with this. Here's an example sentence. This is an RNN, different RNN architectures that are trained for, I'm gonna scroll down to the example that I actually remember. So these are different RNN architectures that are trained for autocomplete. So predicting what the next word is going to be given what you have already typed. And if you put your cursor over a particular character, first of all, it's going to show you what the model predicts the next word is going to be at the top. So over the blue text box, it's going to show you the predictions. And in green, it highlights what are the characters that most influence its predictions about what the next word is going to be. So one cool thing, for example, here to show is that the word grammar appears twice in this example snippet that they show here. The first time that you, so if I put the cursor here, this shows that if I have typed the text up until this, the second letter of grammar, which is R, the network predicts as possible completions, something like Greek, great, or Greece. So this network really doesn't have a clue about what this sentence is likely about. However, this other architecture, the LSTM, you can see that it, and the GRU network, which is at the bottom, you can see particularly visually with the GRU network that when it tries to predict how to complete this word, it's going to look back in its memory, and particularly it's going to look back in its memory where it stored the fact that we were talking about the study of something. And because the word study appeared before, this GRU network predicts words that are, that make more sense in this context, something like gravity or gravitation. And the second time grammar appears, something interesting happens in the GRU network. So if this is the second time grammar appears in this sentence, you can actually see, although it's very light color, that the other appearance of grammar, which is over here, is slightly highlighted, which means that this GRU network was able to remember in its hidden state that it has seen a word like starting with a GR before, it has seen the word grammar before. And because it has seen the word grammar, it made the completion grammar that much more probable in the future. So you can see that this GRU network sidesteps this vanishing gradient problem, and it could remember it could remember characters that came maybe something like 150 characters before a prediction is made. So these long-term dependencies between the two occurrences of grammar is something that a GRU network can do. And even the LSTM network, for whatever reason, in this example, doesn't do particularly well. But a plain RNN would almost certainly not be able to do at all. So you can, I recommend that you play around with this example a little bit more in your own time. So coming back to the lecture, and the remaining part, I just wanted to show a couple example uses of RNNs that have been particularly successfully used between 2015, 2014 maybe, and up until more recently, maybe 2018, 2019, when they have been replaced by a more efficient architecture for a lot of use cases. I showed examples yesterday for generating text, which is obviously, I think, a very natural use case for RNNs, but it's possible to deal with even images using RNNs. And the sequences here can come in different forms. So essentially, when you want to solve a problem with an RNN, you try to find a clever way of turning the problem into a sequential problem. And in this case, in this paper where they were using RNNs for image classification, they were looking at sequentially focusing on different parts of an image and then integrating information from these different parts of the image in order to come up with a final prediction. So here you can see this little square jumping around on this animation is the place where the RNN chooses to focus. And this is controlled by the RNN hidden states themselves. And as it ingests more and more information that it actually sees, it updates where it wants to look at next. A little bit like how humans actively perceive visual scenes by moving our eyes around to search for information. At the bottom of the picture, you can see a similar type of network that was trained to generate images. So here, instead of just shifting your attention from one part of the image to another part of the image, here it's actually shifting this cursor around, and it draws little parts of an image as it does so, and then it jumps to a different part until the image is generated. This is a relatively early example of using RNNs in a non-text context. Here is another example doing this basically in color. It is generating images by essentially moving a cursor around and refining small parts of an image. And this is how you turn the image generation problem into a sequential problem of generating the image bit by bit. Another, in my opinion, very cool example of modeling images as sequences is this work. Actually, there is an earlier version of this work. This is an improved version of something that was maybe from 2015 or 2016. This is training neural networks to paint. And how this works is, imagine that you're drawing an image on your iPad or something. You start from a blank canvas, and then you add individual brush strokes or individual curves as you are creating that image. So you can describe the picture that you're creating in terms of the sequence of operations that you are doing to the image, where each of the operations is a particular brush stroke. And maybe it has, it might be parameterized by a Bezier curve, or the strength with which you're pushing the pencil, or the color that you're using, or the brush type. So here it's shown two sequences of such brush strokes that if you apply them in a particular order, something like a face gets drawn by the network. And here are some more examples of this network drawing faces. So this was trained specifically to draw human faces. On the left, you can see that if you restrict the number of operations that you allow the network to make, you end up with these very nice and abstract representations of faces. If you try to do a face, draw a face very quickly, you're likely to come up with something similar to this, although you're less restricted in terms of the actual curves that you can draw. But you can see that other than all of them being pretty abstract, there is quite a bit of variety that the network has realized can use in order to generate something that would look like a face. If you give it more steps, you can use more brush strokes, then it can get pretty, realistic. Obviously not as realistic as if it was able to edit each pixel individually. And you can also see that this network learns to use different styles. So these are styles that the network learns or discovers just because it was trained to generate images. It learns different strategies in which it can generate a picture. So for example, here, it learns to use rectangles and basically make everything out of rectangles. And then the final column shows the reconstructions. So you can train this network to reconstruct particular faces. This is how it's trained. And this shows the original photo that it was told to reconstruct and the reconstructions that it came up with. So yeah, that's another cool application of RNNs in this for images. And then finally, here is another extension of RNNs for images. Not going to talk too much about it. This is called the Spatial LSTM. It's an extension of the temporal LSTM, where instead of just one time dimension, you now consider the horizontal and vertical dimension of an image, and then you build this three-dimensional LSTM extension. And you can use this also to generate images, and particularly in this paper, they were using it to generate various kind of textures that had some statistical regularities. Finally, and this is I think in the timetable, today's lecture was called Sequence to Sequence, and that was for a reason, is because one of the most successful applications of RNNs have been to map certain sequences to certain other sequences. And particularly in the context of text, this means, for example, translating a sentence to a different language, which means mapping a sentence to another sentence in a different language. When you do sequence to sequence, the basic way you use an RNN is illustrated here. This is from the very original sequence to sequence paper from 2014. So the input sequence is shown here. It's called ABC. And then you have an end of string symbol at the end of ABC. The network starts by digesting the input sequence ABC. And then when it sees the end of string character, it starts to also output outputs. And it starts to output the output sequence that it's going to produce. So in this case, it's going to produce a W. This is going to be using the same process that we talked about last time around how you use RNNs to generate text. So this is going to be randomly sampling a character from a particular distribution that it comes up with. Then this sampled character gets fed back as the input in the next step. So this W is the same W that appeared at the top. Then it generates the next character, which is maybe an X, and then the X gets fed back, and then it generates W, X, Y, Z. And this goes on until it generates its own end of string character at the end. So the way you should imagine this working is that this RNN receives the English language sentence here, and then an end of string character to say that this is the end of the English sentence. And then it starts outputting the French sentence. And then it keeps generating the French sentence until the French sentence ends with an end of string character. And this has been very influential, this very simple idea, using LSTMs, of course. And another trick that Nick is going to talk about next time, which is called attention. Together, these two very simple ideas have enabled Google to completely revamp their machine translation system. So notice that this is a paper from 2016, and the sequence-to-sequence paper, which was the original application to translating text, was from 2014. So in the span of just 2 years, this idea went from the first paper to a full production-ready machine translation system that replaced whatever Google was using previously. And in addition to just this simple idea, a lot of actual hardware tricks went into how do you actually train this thing and how do you run this thing at the scale that Google needs to do this for Google Translate. And this has been a huge breakthrough for machine translation. And now it's replaced by a newer version of neural network-based machine translation, but this has been a very influential moment. You can use something akin to sequence also to map not just to sequences to other sequences, but anything else to other sequences. So here is a paper called show and tell, or a method called show and tell, where the input is an image. It's fed into a deep convolutional neural network. Then this neural network produces a vector, which is used to initialize the hidden state of an RNN. And then the RNN from that initialized hidden state produces a sentence. And this network is trained to produce descriptions of images. So for example, a group of people shopping at an outdoor market. And this is a relatively old paper, but it worked surprisingly well, especially at the time. So you can see that although it makes some mistakes, like this traffic sign, it thinks that it's a refrigerator filled with lots of food and drinks. Not sure if that's, you can read that. But sometimes it was actually very good. So here it describes this image as a person riding a motorcycle on a dirt road. So this architecture was pretty good at being able to translate the information that was present in an image and output a sentence describing that. Another application is sequence to trees, which is you take a sentence as an input and you want to output a semantic tree that, or I think this is called a semantic constituency tree that represents the grammatical structure in that sentence. And this is an important problem in linguistics and natural language understanding. And you can do this by, instead of outputting a tree, which is maybe difficult to do, you output this text representation of the tree, which uses a bunch of parentheses. And you can fit the same problem into the sequence-to-sequence framework. Finally, you can even solve algorithms, or you can learn to implement all kinds of algorithms with sequence-to-sequence, because just like in Turing machines, where you describe algorithms as, you know, this machine that reads inputs from an input tape and then outputs something on an output tape, sequence-to-sequence pretty much does the same thing, but does it with a recurrent neural network. So it's natural that you can describe algorithms using this recurrent neural network type method. So here, for example, trying to solve the traveling salesman problem, which is you're given a set of points and your task is to find a path through this set of points that minimizes the overall path length. And the solution is shown in green on the right. You can similarly use this network where the input is a set of points, P1 to P10, and then the output is the convex hull of these points, which is going to be the polygon that contains all the smallest polygon that contains all the points. and that can be described in terms of a sequence of points, because you know that these polygons are going to be going through the sum of the points in your data set. Another example is triangulation, which is given a set of points, find a way to connect these points with triangles so that none of the triangles are overlapping, and maybe there are some additional constraints on the average sizes of these triangles. And so all of these, by the way, these are examples that come from a paper called Pointer Networks, and this works a little bit differently from sequence to sequence. In sequence, if you want to solve this with sequence to sequence, you would the encoder network on the left which is the first part of the network, would ingest the list of points that are given to it, so x1, y1, x2, y2, and so on, and then it would output a sequence of point indices to define this polygon. It would say 1, 4, 2, 1, which means the polygon goes through point 1, then point 4, point 2, and then point 1 again. The problem with this is that if you want to use this for longer sequences, then the vocabulary that you need to use on the right-hand side, the number of different integer indices that you can output, also grows. And this makes it a little bit difficult to solve for a sequence-to-sequence network. So what this pointer net does instead is, instead of providing character string output, which is different integers, it produces pointers to previous hidden states. And it essentially specifies which particular time step, the point received in which particular time step is the one that I'm going to output. So that's what this picture is going to show. And this is an idea that's related to something that Nick is going to talk about next time, which is called attention, which is one of the another crucial element in improving the performance of sequence to sequence. But I don't want to talk about that because I want to leave it for Nick to introduce that in the next lecture. So that's it. I actually managed to leave 2 minutes, a whole 2 minutes to address questions that you might have.
Brilliant. Thanks, Ferenc. I'll stop the recording and questions.